Thanks for the introduction. Rehabilitation of brain function is crucial for stroke survivors' living quality. For example, motor sensory function. Evaluations and accurate predictions of recovery could enable us to assess and optimize stroke rehab program. However, this mainly relies on behavioral measures. Previous studies have shown that wide matter fiber connectivity from diffusion MRI could be significantly altered after stroke and functional recovery. Compared to behavioral measurements, using wide matter connectivity could help us understand underlying biological mechanisms. The question is, can we inform optimal stroke recovery using tractography-based structure connectivity? A connecton is a comprehensive map of neural connections in the human brain. To construct the connecton, we need brain pulsation and whole brain fiber tracks from diffusion MRI. It has been shown that tractography bias have significant influence on connecting quantification. Therefore, we need to correct this bias for a meaningful connecting construction. The first bias is the endpoint bias. This comes from the fact that streamlines may fail to terminate within gray matter. Here are some examples. Streamlines terminate in white matter or enter into ventricles. This figure shows the streamline endpoints of whole brain tractography. As we can see, streamline endpoints terminate everywhere in the brain, which is not meaningful. It is not good for connecting construction. One way to correct this bias is to use anatomically constrained tractography, or ACT in short. In principle, ACT rejects streamlines terminate in white matter or enter into ventricles. It only accepts streamlines terminate in cortical or subcortical gray matter. By applying ACT, this figure shows more biological meaningful streamline endpoints, which is advantageous to connecting construction. And the second bias is the quantitative bias. This comes from the fact that streamline density is not fiber density. Here's as example, here are two pathways where AB has greater density than CD. When we do fiber tracking, we initiate the streamlines by seeding randomly in both pathways. Because they have same volumes, they will receive same number of seeding points, so the reconstructed streamline density are similar, which does not affect the difference, which reflect the ground truth fiber density. So this is the reconstructed stream density. So one way to correct this bias is to use spherical deconvolution informed filtering of tractograms, or SIFT in short. This figure shows the results after applying SIFT, which makes the streamline density becomes proportional to the ground truth fiber density. So here we emphasize that it is important to apply this advanced tractography method to correct this bias for meaningful connecting construction. So in our study, we used 58 chronic stroke patients. 2/3 of the patients having left hemisphere lesions. Tactile discrimination impairment was evaluated using tactile discrimination test score, or TDT in short. MRI scans, including T1, T2, and diffusion-weighted MRI, were collected in 3T Siemens scanner. For the stroke lesion masks, they were drawn by experienced neuroimaging research. So we used CSD-ACT and SIF2 to generate a quantitative tractogram. And for the connecting generation, we used AL Atlas. So we also generate two different types of connectants. So the first is low-order structure connectant, defined by the weighted streamline count. The second type is the high-order structure connectant, defined by the inter-area correlation of low-order structure connectant, which has been shown in previous studies that those high-order structure connectants are actually more sensitive to in brain disorders. So in this study, we use that to investigate if it provides extra information. And for machine learning, we investigate two different feature sets. So one is the low-order structure connectant only, and the second is a combination of low and high-order features. And we use randomized lasso to select the features. And we use the leave one out cross validation for our machine learning model validation. So here's the gray matter pulsation from AL Atlas. And here, this figure shows the key features extracted from our machine learning model. So here, blue lines for low-order features, and the purple for additional high-order features. So this figure here shows, as we can see, so the most connections, most features actually connect to left hemisphere, which is consistent with our cohort. That is, they have a dominant lesions in left hemisphere. We further look at the brain regions connected by the key features, and we then subgroup these features into sub-brain systems. So, for example, here we find this mainly relates to motor, motor sensory, and spatial information processing, which are closely related with motor sensory tasks. In addition, we also find some secondary sub-brain subsystems. So, for example, visual and emotion brain functions. So this figure shows the relationship between the predicted TDT score and the true TDT score, with the blue dots representing the low-order features, and the orange one represent the additional, the combination of low and high order features. And we can see it's very clear there's a correlation between specific white matter disruption and the sensory deficits. So to conclude, we provide a connecting approach for improved understanding of the biological underpinning of structural network disruption in stroke survivors. Specifically, we use the quantitative tractogram reconstruction, and then we use the machine learning for predicting the TDT scores. Our results show that we identified structural network disruption are actually associated with sensory discrimination ability, like The primary findings is the motor sensory, spatial information processing, and the secondary is like a visual motion. Based on this understanding of affected the white matter connections, our study could provide a potential improvement of rehabilitation program. Thanks for your attention.